Hello there. It is the 28th of August, 2023. It's a Monday. My name is Peter Harpending. I'm making this video. I'm getting paid to make this video by the Eternity Foundation. Eternity is a cryptocurrency. I hate telling people it's a cryptocurrency. I prefer saying it's a payment network because the cryptocurrency brand is toxic, and that actually kind of brings me to the topic of this video, I suppose. Or the, I guess, topic of this channel, which is that, cryptocurrency is basically this, world of fake hype and, bullshit. But, there is a kernel of, I guess, truth or reality at the bottom of the lake of bullshit. I kind of assumed cryptocurrency was kind of all hype. And then Craig Everett, who's the other developer on the Vanillae Project, we'll get to what Vanillae is in a minute. It's a long story, but we decided to make just a very basic idea, which for some reason nobody had tried in the world of crypto, which is let's just make a very simple e-commerce website where you can buy and sell just, ordinary goods, like baby bottles or, waffle makers or whatever, or GPUs, using cryptocurrency as a payment system. And I believe we tried a different business idea using, we tried to use Ethereum. We looked into a few other coins and they weren't. The issue with crypto, like the question is why is there so much bullshit and why is there so little real usage cases? And I think that's really the question I want to address. And I think crypto is kind of where the World Wide Web was in like the year 2000. I'm too young to remember, but I think that's about when the .com bubble burst. I think the crypto bubble has kind of burst. And the World Wide Web wasn't bullshit, but the .com bubble was. And there is a kernel of truth at the bottom of this, at the bottom of the lake of bullshit. And, it's the size of a popcorn kernel at the bottom of Lake Superior. And the problem with the .com bubble was basically the hype got way ahead of what the technology was actually capable of delivering. And crypto has suffered a similar fate, in my opinion, which is correct. And that's basically that there isn't. Here's the question: is why can't you buy groceries with Bitcoin? And basically, the answer is that it's too slow. It really scales poorly, and if more people tried to use it, it would scale even worse. It basically has this linear scaling problem. And so, all sort of peer-to-peer networks have this basic problem, and then there's a question: okay, is there a way to get around this? Could we make crypto actually useful? And we kind of, after Craig and I, this is 2021, we tried this other business using Ethereum, and we just like, there's just no way. And one thing leads to another. Craig ends up getting hired actually to work for the Eternity Foundation, I believe, as a core developer. And, we kind of look into this and we're like, hey, this one's actually, it's faster than credit cards and it doesn't have these scaling problems. And so we decide to try out we spent the year 2022 making Aegora. And what we discovered making Aegora was that the actual chain itself, the smart contract language, which is called Sophia, the, Sophia compiler, the actual, blockchain protocol, all the, internal stuff that only the core developers really understand, that stuff was all very solid, and the core team is really, really, really good. They're really, really smart people. The tooling to talk to the blockchain from the outside world, so from, let's say, Aegora, was just, it was not very good. And so in the process of developing Aegora, we ended up kind of developing the tools that we wanted to use. And it wasn't just that the tools were bad, it's that the entire sort of infrastructure and thought process that went into the tools, everything about it was wrong. And so we've basically been working on developing our own ecosystem for better tooling. And, ultimately our goal with this is we want, if you want to sell, I don't know, you have a website, you want to sell your feet pictures or something, and you want to just take crypto, you just want to start a business. We want you to be able to just do that. We want a child who wants to set up a lemonade stand, we want that child to be able to take crypto, and we want it to just be that easy. And the thing is, I'll go on walks and I always will encounter like little kids with lemonade stands, and I don't carry cash with me. And I always feel bad. I'm like, well, do you take credit cards? And no, and I don't have cash. And so I always have to like go home, find some cash, and then go back to the lemonade. And it's just, and I think, for little kids, that the sort of elimination of cash from the everyday world has had this interesting effect of sort of like robbing those types of experiences from people. Little kids can't open a lemonade stand anymore. Anyway, but you could with Eternity, in theory, if people used it. And the problem, the blocker for that is that the tooling isn't very good. And so right now our goal is, so we built the tools that we wanted to use. In particular, I don't have it installed. Here. So, particular, we built from Aegora's backend, so the server that's running in Japan. We Craig built a application, an Erlang application. So think a library. Application means a specific thing in the world of Erlang, to talk to the blockchain from our backend, which is written in Erlang. And then I built this page script to talk to the browser extension. And I know it kind of sounds like a trivial task, but it took me like 6 months because it was just, okay, we don't have to get into that. So anyway, we're building the tools we wanted. The documentation, some of it's good, but you kind of have to know where to look. And basically, whenever there's something I want to know, I basically have to go on this Slack and ask the core team, and somebody knows where the docs are. And so we're building the docs we wanted, which is hopefully what I'm going to get to today. And also the video tutorials we want, which is this. And so I guess that brings me to the main topic of today's video, which is Base64 versus Base58. Now, in the process of developing stuff, so right now I'm developing a new browser extension wallet, and in the process of trying to develop whatever you're doing with Eternity, you're going to come across these like stupid things that really should take like an hour to figure out, but really take like 6 hours. And so this is one of those things. These are two, so what these are, computers of course represent their data as ones and zeros, which is so-called binary data. And we also, sometimes we want to communicate binary strings as plain text. So an example of where we might want to do that would be, here, I can actually give you a concrete example. What? Jesus Christ. Okay. Okay. Let me see if this works. So Jack Russell, which is the wallet I'm building, it generated a public key, and it has this AK underscore and then a bunch of random letters and numbers. And the question is, what are these? And what this is my public key. And we'll get into how. By the way, another thing that I wish existed was kind of a appropriate depth dive into the mathematics of how cryptocurrency works. Because it's complicated, but it's also not that complicated. Now, there's a lot of theoretical context, particularly algebraic geometry, the geometry of elliptic curves, which frankly I don't know. But kind of the basic ideas, how asymmetric cryptography works, how, something like the Euclidean algorithm works, how, let's say, the idea of the discrete logarithm problem, what all of those things mean. Certainly that's something we can get into. So let's see. So what all this, so this is just a prefix that so my public key is 32 bytes. So that's whatever 32 times 8 is, that many bits. So a bit is a 1 or a 0. That's however many bits of data, plus there's 4 bytes at the end, which is a checksum to make sure that you didn't screw up input. So I don't have a paper book nearby. On paper books, there's this ISBN number at the back, and it actually, the last digit of the ISBN number is actually a check digit. So the idea there is that if you enter in the number wrong, it will tell you yes or no that this is a valid ISBN number. Credit card numbers have a similar thing. What was I going to say? Anyway, so this is 32 bytes plus a 4-byte checksum, so 36 bytes, encoded using, so again, ones and zeros. Actually, a byte is a number between 0 and 255. Just a sequence of 36 bytes encoded in plain text. And again, what does the word encoding mean? This is actually a useful thing. So to encode something means to take something that is sort of clear and make it cryptic, or something that is cryptic and make it clear. And so you're saying, okay, well, why is binary data? Binary data seems more cryptic than plain text. But again, whenever we pick a direction for this verbiage, so this could just as easily be called decoding, and the opposite direction going from this to the public key could be called encoding. But by convention, whenever we're picking this verbiage that has a directionality to it, a forward and a backward direction, we always talk from the perspective of the program. So from the perspective of our program is reading memory. Memory is just bytes. To the program, this is a bunch of nonsense. And the actual public key, the 32 bytes, is the interesting data. So what we're going to talk about is how these two algorithms work and how they differ. The most important thing to understand here is that these are not the same algorithm. So when I came into this, I started with Base64 because this is the much simpler algorithm. And I assumed that there was sort of a general base N algorithm, and these were two instances of the same algorithm. And that's not true. So Base64 is the easier one. Like I said, it treats your byte array as a stream. So let me look at this diagram. So I think this kind of illustrates the whole idea. So you imagine we have 3 bytes here, and this is the same byte string. So what this does is it splits the bytes up into, so Base64, it splits the bytes into 6-bit chunks. And maybe we should talk about how to read binary. Do I want to get into that? Not really. Okay, each of these 6-bit chunks represents a number, and I'm not going to, I should get into how this works. I guess we will have to for Base58. So Base58 is the general base N algorithm. And base 64 is actually the special case. And the special case is because 64 is a power of 2. We'll get into this. Anyway, so each one of these 6 bits, 2 to the 6th is 64. So 6 bits, and much in the same way that, let's say, if we had 2 decimal digits, we can represent any number between 0 and 99. And that's because 100 is 2 to the 2nd power. So, or is 10 to the 2nd power. So the base to the number of digits, that is the base to the number of digits minus 1. So for instance, 10 to the 2nd power is 100. We can represent any number between 0 and 99 with 2 decimal digits. So every digit can represent a number between 0 and 9. Every digit can represent a number between 0 and 9. And then any time, so with 1 digit, there are 10 possible values. Oh, here's actually the base case. With 0 digits, so 0 base 10 digits, there is 1 possible value, which is 10 to the 0. With 1 digit, there are not 10 possible values, 0 through 9. With 2 digits, there's 100 possible values, 0 through 99. With 3 digits, there's 1,000 possible values, 0 through 999, and so on. So the number of possible values you can represent using a base B is the base to the number of digits. So with base 2, it works exactly the same way base 10 does, but instead, so with base 10, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are sort of 9 distinct symbols. You know, they could be any digit. They could be letters. We could do A through J. Is that the 10th letter? Doesn't matter. A through J, I think. And then instead of K, we would just loop over and start and, you know, put down so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we're out of digits. What we do is we put down a 1. There's an implied infinite string of zeros. We can put down a 1 and then start over. Then we put down a 2, start over, put down a 3, start over, put down a 4, start over. And then when we get to 9, okay, we're out of digits, so we put down a 1 and then start over from 0, 0. It's exactly the same idea. So with binary, which is base 2, instead of 9 distinct symbols, we have 2. So the way you can actually count in binary on your fingers. So 0, 1, 2, 3. Okay, we're out. So I don't want YouTube to censor me. 4, 5, 6, 7. Oh no, we're out. 8. Okay, and then we just start over. 9, 10, 11, 12, 13, 14, 15. It's actually a fun exercise. And you could count all the way up to 2 to the 10th, which I don't know how many what that is. It's like 1,024 or something like that. Might be, I don't know. It's a 2 to the 10th. That's 2 to the 10th minus 1 is the max that you could represent here. And that's just how binary works. So in particular, 2 to the 6th, put up 6 fingers. This is 63. This would be 64. So base 64 means instead of, so really what we call binary with computers, that's more of a human-friendly abstraction. Really, computers go by bytes. They store data in bytes, which are 8 bits, but the bits are not really fake. The bytes are what's real, the bits are fake. Computers really are base 256 machines. That's the way to think about it. Computers represent data in base 256. And at least from the perspective of our program, that's the way data is presented to us, is in base 256. And all data in your program, including this video, including every text, everything you've ever watched, all of your feet pictures, they're all just long strings of numbers between 0 and 255. And then there's conventions for how you go about like structuring those numbers. And that tells you what the data means. But the data itself is always numbers between 0 and 255, and you have however many of them you need. And so from a human standpoint, we pretend that these are actually 8-digit long binary strings. So what Base64 does is it splits these 8-digit strings. It operates 3 bytes at a time. It takes 6 bits, 6 bits, 6 bits. So it takes 24 bits, and instead of 3 groups of 8, it regroups them into 4 groups of 6 bits. Each 6-bit string can represent a number between 0 and 63. Each one of those numbers between 0 and 63 is assigned to a letter, a number. There's a table on Wikipedia. Here, let's find it. Yeah, there's this table on Wikipedia here. Hopefully that's big enough for you to see. So maybe we can compare, actually. So this binary string turns out to represent the number 27. So we go to 27 here. And that corresponds to the character, the letter, lowercase letter b. Upper and lowercase characters are distinct. This binary string corresponds to 33, which is H. This 6-bit string corresponds to the number 54. Where's 54? Which is the character 2, not the number 2. And again, these characters internally are, of course, binary strings, but again, so it's kind of a confusing thing. So we're basically taking data in one binary format and converting it to a less space-efficient binary format because we want to put that in plain text. And so in plain text, we have this convention called ASCII. Okay. And in ASCII, you'll notice every number, you get numbers between 0 and 127, and then there's a bunch of other crap that doesn't matter. I think the convention is you start with a leading 0. I don't remember how it works. Anyway, between 0 and 127, there's all these different characters. So, for instance, 2, this 2 here, so we encountered the string 54, and really when we go to encode that, we just write down the character 2, which actually just means the byte corresponding to 50, the number 50. 63, we write a slash, and the slash really corresponds to the number 47. So we're basically just, for kind of weird reasons, taking this binary string and encoding it using plain text. Okay. There's kind of an issue with this, which is that if we go on Base64, so this algorithm is very straightforward. You should be asking, what if the length of my binary string, so this works perfectly if the length of our byte string, if the number of bytes in it is a multiple of 3. What if it's not? Okay, in that case, there's this convention where basically there's this padding character, and we'll get into the details of how that works. But basically what you do is we'll get into how that works. Okay, what I want to talk about instead is Base58. So we'll get into how this works. This is really simple. This one is if you are a programmer who is pretty comfortable handling binary data, irrespective of the language, and we'll get into code examples in a minute, irrespective of what language you prefer, if you're kind of comfortable dealing with binary, whatever the representation of binary data is in your language, it's very hard to screw this up. And if you do screw it up, you're going to screw it up in some subtle way. This is a very straightforward algorithm. The only part that's a little bit annoying is the padding. And then, okay. Base58, oh my goodness, this one is so easy to screw up, and there's so much stupidity here. Okay. What Base58 does is it takes the entire byte string, the entire thing, and thinks of the entire thing as a long integer. So here, there's a very crucial difference. The way Base64 works, it has this sort of fire and forget property. So it reads 3 bytes, encodes it. Okay, I don't care about those anymore. Read the next 3 bytes, encodes it. Don't care about those. Read 3 bytes, encode them. Don't care about them, and then kind of just concatenate all the results. So it has this property where it scales linearly. Base58 requires you to take the entire byte string and think of it as a long integer, as a really, really, really big number. So in this case, this entire 24-bit number corresponds to, in the decimal representation, the number 7,216,575. And then what we do is encode. How the hell do I phrase this? We use the standard long division algorithm that you learned in school. What that number is actually a way to find the decimal representation of a fraction. That's what long division is. It's the way to find a decimal. Let me rephrase that. So when you take a number like 3/7, what long division is presented to you as when you are in school is a way to calculate 3/7. And we're going to get into a little bit more about how math works. But from the perspective of math, a lot of subjects have this property that when you understand the subject, well, and I'm not claiming to be an expert in mathematics, but, I know way more than an average person. Once you understand the subject, your perspective on how the subject is actually structured is very different. And it tends to conflict a lot with the way that the subject is taught. So when you learn this long division algorithm in school, it's taught as a way of computing a fraction. Really what it's doing is taking a number like 3 divided by 7. Now, from the mathematical perspective, the actual way that you write the number down is not important. What matters itself is the actual number. So 3 is an abstract quantity, 7 is an abstract quantity. How you go about writing that on the page, it doesn't matter. You could use Roman numerals, you could use decimal notation, you could use binary, it doesn't matter. 3 divided by 7, that is the primary data, is the pair of numbers 3 and 7. And then there's a convention for deciding that 2 fractions are equal. So in particular, for instance, like 3/7 is the same number as 6/14. Okay, and so there's a way of deciding that if I have one pair of integers and another pair of integers, deciding that these two refer to the same rational number. So a rational number is a ratio. That's what it means, is a fraction of 2 integers. And the second integer is not allowed to be 0. So the bottom of the fraction is not allowed to be 0. The top can be 0, but not the bottom. And the reason is just dividing by 0 always breaks basic logic of mathematics. And it doesn't, it's a long story. Sometimes you can divide by 0, but most of the time you can't. What was I saying? We're talking about base 58. So what long division is a way of computing. You have integer a divided by integer b. And what you're doing is computing the representation of a divided by b as a decimal in base 10 notation. That's what long division does. Here, what we are doing is taking this integer. We're really taking this integer divided by 58. It's not, whatever. We're taking the integer and we're finding the base 58 representation of that integer. So instead of a sequence of, so when you compute 3 divided by 7, you compute a sequence of digits, each ranging between 0 and 9. Here, we're taking this integer, and again, we're not thinking about this the decimal representation of this integer. We're thinking about this integer as this like abstract thing that we can't put in like concrete terminology, or that doesn't have necessarily a concrete representation, or that has many different concrete representations that are equivalent. And we're saying, I want to take this integer and represent it as a sequence of digits between 0 and 57. And base 58 has a slightly different alphabet. So the motivation for base 58 was that there's a lot of cases here, for instance, the capital letter O and the numeral 0. It'd be very easy to conflict those two. Or for instance, the digit 1 and a lowercase l. And so what it does, so base 58 is the same basic idea as base 64, but these digits, these problematic digits, have been removed. Additionally, plus and slash have been removed because the idea was that, and equals. The idea was that maybe you would be putting like, let's say, a public key, you would be emailing that to somebody, and your email program might see plus or slash and terminate the line and put the rest of the key on the next line, and so there could be a copy and paste error. And so it's trying to eliminate that. But because 58, so if you wanted to make this easier, you would actually just you could eliminate the problematic characters, and then you would eliminate whatever 58 minus 32 is. Base 32 would be really easy because, oh no, it wouldn't be. Yeah, base 32 could work, because instead of going off of 6 digits, you would go off of 5. And 5, yeah, then you would have to go, the least common multiple of 5 and 8 is, oh, that's so stupid. The least common multiple of 5 and 8 is 30. Wait, what? Not 30. 5 times 8 is 40. So you'd have to go 40 digit. You'd have to operate on 40 bytes at a time. Or you could do this, which is hex encoding. So what this is this hexadecimal encoding is the same idea as base 64, but it goes 4 bits at a time, and then it doesn't need this padding because there's no chance of having it lines up perfectly with each byte, so it goes 1 byte at a time rather than 3. And so if your data will always be an integer the number of bytes you have will always be an integer multiple of 1. So that's base 16, which is 2 to the 4th is 16. That's what this is. And so if you've ever done like HTML and you've seen the notation for colors, that's one, it's 6 numbers and letters. The first 2 are a number between 0 and 255. That refers to how much red is in the color. The second one is the amount of green. The third one is the amount of blue. It's RGB notation for colors. Okay, so that's the difference between these two algorithms. Base64 is sort of thinks of your data as a stream of bytes, and it goes 3 bytes at a time, encodes those 3 bytes. How long have I been talking? 35 minutes. That's great. It goes 3 bytes at a time, encodes those 3 bytes. Let me put this. Let me minimize it. Encodes 3 bytes at a time, forgets about them, moves on. 3 bytes at a time, forgets about them, moves on. Base58 has to take the entire byte string into account, think of the entire thing as a number, and then encode it in using your sort of standard long division algorithm that you learned in school, and we'll get to that in about why that works. So, So, like I said, Base64 is simpler. It treats your byte array as a stream of bytes. It encodes 3 bytes at a time into 4 characters. 3 bytes is 24 bits, 4 groups of 6 bits, which is 4 letters. There's a table here to convert 6-bit integers to letters, which you can look up on Wikipedia. There is also a padding rule to deal with byte strings whose byte length is not a multiple of 3. Base58 is more complex. Roughly, Base58 thinks of the byte array as a very long unsigned integer. Unsigned just means that unsigned means it doesn't have a sign, so we're not considering negative numbers. I'm not going to get into how computers represent negative numbers. Not doing it. And then encodes that integer into Base58 using the normal quotient-remainder algorithm, which I apparently explained below. I wrote this post, like, when did I write this? March. Okay, wow. So notionally, the idea is we have a byte array, and we want to encode it in Base58. So what we do, what this line does in Erlang, is this is a pattern match. So the two greater than less than signs. This says this is a binary string. So what I'm doing is I'm computing the bit size of the byte array. So how many bits long is it? And I'm taking that number. Basically, what this is saying is consider the entire byte array as a single number, which is named n. Okay, so this is now a big integer. Now Erlang is nice. I have examples in 2 languages, Erlang and TypeScript. Now my official reason for choosing those is that those are the 2 languages we use in Eternity. Luckily, both of those languages have data types in the language in the standard library for integers that are an arbitrary size. Most languages have integers as a fixed size. So when I was a child, computing switched from it was a big deal to go from a 32-bit operating system to a 64-bit operating system. What that meant was that the size of an integer, as far as the computer was concerned, went from being 4 bytes long, which is 32 bits, to being 64 bytes long, or 64 bits long, which is 8 bits. 8 bytes. Is that right? Yes. So god damn it. 32 bits, 4 bytes. That was what an integer meant in as far as the processor was concerned. When we switched to 64-bit, that meant that suddenly an integer was 8 bytes long, 64 bits long. Now, why was that such a big deal? The maximum number that you can represent with 32 bits is 2 to the 32 minus 1, which is roughly about 4 billion. This has a lot of, and with 64 bits, it's some gargantuanly huge number. So it's 4 billion. What, to the, it would be 4 billion squared, right? Yeah, if you take 100 squared, it's 100 times 100 is 10,000, right? Yeah. So 2 to the 32 squared would be 2 to the 64th. Yeah. So it's 4 billion squared, which is a very, very big number. The reason that this is important is that, again, everything in a computer, all important data is stored as integers. So in particular, your computer has what's called RAM, or random access memory, which is basically working memory. So when I'm talking, I have sort of long-term memories, things that happened yesterday or 3 days ago or 10 years ago, and then I have kind of things that I'm juggling in my head that I'm kind of planning the next 20 minutes of whatever I'm going to talk. That's roughly kind of what RAM is. RAM is stuff is data that programs on your computer are using right now. And again, those data are just bytes, and each byte in memory has an address, and that address is simply an integer. And so if your integers were 32 bits long, that meant that the maximum number of bytes you could have in RAM was 4 billion, roughly, or 4 gigabytes of RAM. Now, in 1980, 4 gigabytes of RAM was just unthinkable, so this restriction was fine. Let's see, 4 gigabytes of RAM. So the reason we switched to 64-bit operating systems was because hardware got good enough that we wanted to be able to have more than 4 gigabytes of RAM. And specifically, we wanted more than 4 gigabytes worth of memory addresses. And so that's why we switched to 64-bit computers. Not only that, the way that we represent time in computers is we just count the number of seconds since midnight UTC time on January 1st, 1970, I believe. Okay, how long is 4 billion seconds? It turns out that is, I'm bad at math, 68 years, something like that. No, it's signed, so it's actually 2 billion seconds, roughly. So what that meant in particular was that computers, this is called the 2038 problem, is that computers would run out of time in 2038. So if you remember the Y2K bug, most of you are probably too young to remember that. I'm too young to remember that. This was this fear that because we were using two decimal digits to represent dates, so instead of 1998, we'd use 98. And then what happens when we get to 2000? Now there's an ambiguity. And that turned out the bugs all got fixed before that became an issue. We have a similar issue with 32-bit time, and I think that's mostly been fixed. That was called the 2038 problem. I doubt human civilization will last that long, but anyway, so we switch. The point is that most languages have integers that have a fixed byte length. Erlang and TypeScript are both very nice because integers in Erlang have an arbitrary byte width, which is nice. You don't have to worry about it. And in TypeScript or JavaScript, I think by default all the numbers are floats or something like that. I actually don't really know. It's very confusing. I don't really understand JavaScript. I don't think anyone does. But there is a type in the standard library now to represent arbitrary length integers, which means that our job with Base58 is a lot easier. So let's, I'm going to actually switch. Let me, sorry, I have two terminal programs. There we go. Okay, so this is more or less the same program. So, but here we have more comments. So this is how to encode binary data into Base64. And I'm only going to show Erlang. You know what? I will show, maybe I'll show TypeScript if I feel like it. I'm not sure. But Erlang, it's a lot clearer just because the notation just allows us to pick it apart. In TypeScript, what you have to do is you have to do this dumb thing where you take the bytes and then you create 6 new bytes or 4 new bytes and then do these bit shifting operations to get everything to line up. And it's very stupid, whereas Erlang just allows you to kind of directly express your idea using the notation of the language. Okay, so we have binary data. We want to encode it in Base64 notation as a string. 1 second. All right, we're back. So like I said, we're taking our binary data. So this is our string of digits between 0 and 255. And we're converting that into a sequence of characters. So encode, again, from the perspective of the program, binary data into Base64. So in general, the general case, we have at least 3 bytes remaining. And so I've written it like this: 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, G, whatever, blah, 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 and then the rest. So what this notation means is that we're taking the first, let me see, is that big enough to read? That's definitely big enough to read. Okay, we're taking the first 6 bits here, putting that in the integer A, taking the next 6 bits, putting that in the integer B, the next 6 bits, putting that in the integer C, the next 6 bits, putting that in the integer D, and the remainder of the binary string, which could be empty, because this could be the end of a binary string that where the number of bytes is the byte length of the byte string is a multiple of 3. So rest could possibly be the empty byte string. But this is the general case, so there are at least 3 bytes remaining, 3 or more. And what we do is we take those, and these are just integers, A, B, C, and D, and then we convert these to characters. So the character of A, the character of B, the character of C, and the character of D. Int to char just is looking up the integer in a table. This is just a table. And what this is saying, so again, strings in Erlang are just lists of characters. And so we're taking the character of A, the character of B, the character of C, the character of D. So we're converting 3 bytes into 4 characters, saying make that into a list, and then can prepend that onto the result of encoding the rest of the list. Okay. When we have 2 bytes remaining, so exactly 2 bytes remaining, we take, so we have 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, G, F, G, H, and then nothing. So what we do is 2 bytes, that's 16 bits, 6, 6, and 4. And so what we do is we do 3 characters, we pretend these are zeros, and then the last one is just going to be an equals. So we're going to convert these to characters, the character of A, the character of B, the character of C. Again, so we bit shift this to the left. That's what BSL means, bit shift left by 2 bits. And then we put an equal sign to indicate that there are... am I recording? I am. Bit shift this, or then we put an equal sign to indicate that there are, that this sequence of, when we get to decode, it'll make sense. But if we see one equal sign, we say, we're decoding 2 bytes. If we see 2 equal signs, then we know we're decoding 1 byte. Okay. So convert all of these to characters, and then say, okay, the result of this is the character of A, the character of B, the character of C. And okay, by the way, in Erlang's a functional language. Like most functional means function-oriented, so you write your programs as mathematical functions. We'll talk about what that means, what mathematical functions mean. But what that means is that in a function body, so what this is branching. So this is like if then else. So enc, if it matches this, great, then we execute what's in here. If it doesn't, we try the next branch. Does it match here? Cool, then we try here. Does it match here? If not, here. So if it does, if this case matches, then we go in here. If this matches, then we go in here. And if none of them match, the program crashes. That's how branching works in Erlang. We don't tend to see much of if then else. So it does happen, but generally speaking, when we're doing branching, this is the way that we do it. Is we have some data. Is the data shaped like this? If so, do this to it. Is the data shaped like this? If so, do this to it. And it ends up being, very nice. So if the data is shaped like this, we do this. If the data is shaped like 2 bytes, so if we have 2 bytes, then we do this. If the data is 1 byte, we take 6 and 2. We take 6 bits and 2 bits. We bit shift this to the left by 4 bits. So we put 4 zeros there, binary zeros. Convert them to characters, the character of A, the character of B, 2 equal signs, and then we're done. And like I said, up here, rest could have been an empty byte string. And so in this case, when we call encode of rest, it's going to check, okay, does it match here? No, we don't have 3 bytes. We don't have 2 bytes. We don't have 1 byte. We have the empty byte string. Cool. Then this is the empty list. And that's how encoding works. So how does decoding work? So this is important. So decoding base, so we have a Base64 string, and now we want to decode, get back the binary out of it. So we decode the Base64 string, and so Erlang, again, most functional languages don't have variables, so they don't have mutable states. So if I say x, here, let me just actually give you an example. So if I say x is equal to 3, and then on the next line say x is equal to 5, it says no. X is equal to 3, x is 3, and that's the end of the discussion. Compare this to, let's say, Python. If I say x is equal to 3, and then I say x is equal to 5, x is sort of a placeholder, and I can update it. You can't do that in Erlang. When you say x is 3, x is 3. So in particular, if you want to have some sort of state that you sort of update, what you do is you sort of pass it in as an argument to a function, and then sort of have the function call itself recursively over and over. So in our terminal case, this is the decoding. So we're going from our Base64 string to binary. So terminal case, we have 2 equal signs at the end. So again, you have to, we'll see. The reason that we don't put the general case first is because in this case, up when we were encoding, if we have 1 byte remaining, it will not match on the 3-byte case. But here, if we have 3 bytes remaining, then we match on 4 arbitrary characters. Y and Z could be equal signs. And if we put this case first, it would match. So instead, we put the special cases first. Ordinarily, it's advisable to put your general cases first because you want to put your most frequent, you want the things that occur most frequently to occur earlier in the branching logic. So that was why up here I did that, because just for performance reasons. But down here, we don't have a choice. Okay. And there's no efficiency to be gained by like saying WXYZ, where Y is not equal to this and Z is not equal to this. Z, where Y is not the equal sign and Z is not the equal sign. Because it's still running these checks no matter what. Okay. If you really wanted to be a performance guy, you could make this a little bit more efficient. But again, this code is illustrative. By the way, Erlang has a Base64 library in the Base64 module in the standard library, and so in practice, you should use that. This code I just wrote for educational purposes. So the terminal case, we have 2 equal signs at the end, and that's 1 byte or 8 bits remaining. So WX equals, we convert these to numbers by looking these up in our character to integer table. So our characters are WX and 2 equal signs. We convert these to our 2 numbers, and then we regroup them. Using our Erlang binaries. So W and X, these are characters, equals, and then our accumulator. Our accumulator is our state. So again, we're looking at the terminal cases first, and then the general case will recursively call decode. So again, Erlang, we don't have variables, so we also can't have loops. And this seems, if you're coming from the world of imperative programming, you know what? I think I am going to do the TypeScript just for the people who come from the world of imperative coding. And it's, even though Erlang to me seems a lot simpler and a lot more clean, if you're not wired to think in a functional way, it's a little bit jarring to wrap your head around. And a lot of people just cognitively don't have the machinery to understand recursion. If that's you, then you probably shouldn't be programming, especially things that handle people's money. So decoding WX equals. So the number of W is character to integer, number of X is character to integer of X. And then so what we say is the last byte of our resulting byte string, which is 8 bits. The rest here must be zeros. So we're asserting, this is a crucial point. If the data on the right, this is both saying, take the data on the right and disassemble it into the shape of the data on the left. And if it fails to disassemble like that, so for instance, if there were anything other than zeros here, this is also an assertion, and the program crashes if the assertion fails. And Erlang is a highly concurrent language. So, the idea is that you have a program and there might be tens of thousands of threads running. And so if you have tens of thousands of threads running, if one thread crashes, it's really not that big of a deal. So in fact, if you're running, if you come from any language other than Erlang, crashes are the worst thing that can happen in your program. And so you basically want to avoid them if you can. and you go to a lot of effort to make sure your program doesn't crash. Whereas in Erlang, because we have this very highly concurrent system with tens of thousands of processes running at any given time, we actually like our processes to crash. And so what we do is we put assertions everywhere. And so if everything isn't exactly right, the process crashes. The consequence of that is that if the process is still running, that means it's running correctly. And so you end up getting fewer bugs, because if something goes wrong, the program doesn't try to recover from that, it just dies. And so, yeah, that's the idea. Okay. So this is the case where we have 1 byte left. So 2 equal signs means 1 byte left. Okay. So now we're decoding. Oh, we have 1 equal sign. That means there's 2 bytes left. So much in the same way, our input characters are W, X, Y, and equals. We convert these to numbers using exactly the same procedure. Regroup them using, it's exactly the same idea. And the result is our accumulator concatenated to the first byte and the second byte, and then we're done. The terminal case, we have no bytes remaining, so this would happen when we were decoding a string and the byte, and so let's say we had a byte string and the number of bytes was a multiple of 3. So when we encoded it in Base64, there was no padding left. Okay, and now we're going to decode that again. This is saying, okay, this is the case. The general case would consume the end of the string, because the general case applies when there's 3 or more bytes remaining. So in particular, if the number of bytes that it's decoding is a multiple of 3, the general case will consume the end of the string, and then when it calls itself again, it'll say decode the empty string, and the state is our accumulated state. It just says, okay, we're done, return the accumulated state. Okay. So our input is W, X, Y, and Z. We convert these to numbers using exactly the same procedure. We decompose these in exactly this way. So decode W, X, Y, Z, and we're pulling these 4 characters off the beginning of the string, and we're taking the rest of the string and putting it in this variable rest. This is our accumulated state. So when we called into this function, we called into decode. So by the way, functions in Erlang that are the name of the function and the number of arguments it takes. So decode, that takes 1 argument. That's called the arity of the function. Decode 1 is a different function than decode 2. So this is a very common pattern. You have decode 1, which is what you would call from somebody outside the program, and then decode 1 says, well, I'm going to do something to this input that builds up some accumulated state and then returns the accumulated state. So what I'm going to do is I'm going to call decode 2 with the initial state, and then, yeah, you get it. So this is saying, call into here, this is the initial state, and then there's implicit return. So there's whatever is the last thing in the function, you can put the word return in front of it if you're coming from another language like that. Okay, so decode W, X, Y, and Z. These are our 4 characters, the rest of the string, and our accumulated state. We convert all of these to integers, so that's this step. Our new accumulator. So I didn't bother putting the decomposition on a different line. I just said put the bits in this way, and then saying, okay, now we're going back, saying decode the rest of the string. Here is our accumulated state. Okay. And so the function never terminates if this branch matches. If this branch matches, we're calling the function again. And so this is and when the function terminates, it's going to be one of these 3 cases. Okay. And in these cases, you can see there's no recursion. The function isn't being called again. That's the end. And similarly up here. So here, if this first branch matches, we're not terminating. This has an implicit accumulator in it. So again, if we can do this, this is slightly more efficient, and I think a little bit clearer. So this is saying, you know, okay, call the function again, and then when the function terminates, it's going to be one of these three cases. Okay, so that's encoding and decoding in Base64, and then our integer to character tables. This $ notation means so $F, for instance, if we go back to our ASCII table, $F means, it was little f, right? $F means we find F here and we say, okay, what is the ASCII number? Oh, wait. Oh, I was reading off octal values. I'm stupid. Oh, I'm stupid. Anyway, what is the ASCII value corresponding to F? Okay, this is saying this is the integer 102. So again, there's kind of this weird kind of circularity to it that might be a bit confusing. Okay, that's what this means. And then character to int is exactly what you expect. Okay, that's Base64. That's the simple case. Okay, and like I said, if you're doing this in a language that doesn't have big nums are those arbitrary length integers that I talked about. Good luck, because you have to code big number arithmetic in your language. Okay, this is probably adapted from this file, I believe. Okay, so there's a couple references here, which I will try to remember to link. Okay. And so I have some test cases. Forgot about that. Okay. Yeah. So there was a YouTube video that I watched that apparently made this clearer to me. So let's. That's right. I forgot about that. Oh, that's so annoying. Okay. So remember how we talked about with our standard integer notation that there is an implicit, so when I say the number 10, if I write down 10, 10 in binary notation, that is the same number as 010, which is the same as 00010. So with numbers, when we're writing down a sequence of digits that corresponds to a number, there's an implicit infinite string of zeros at the beginning of the number. What happens if we go back to our diagram here? What happens if we're encoding a byte string and there's a bunch of 0 bytes at the beginning of the string? When it starts to consider this as a number, it won't consider those leading 0 bytes to be data. Right? And it's so annoying. So we have to have a special case for leading 0 bytes. And the way that this works is we call this function split zeros. So, okay. So split zeros takes bytes and the initial zeros, which is an integer, and it returns the number of leading zeros and the remainder of the string. So this just chops. Okay, so that's what this does, is it looks at our byte string. So this is encode. We're going from bytes to Base58. It looks at our byte string and says, how many leading zeros are there in the byte string? And it returns however many there are, and then it says, here's how many zeros I counted, and here's the remainder of the byte string. Okay. So we have our binary string, and our initial zeros. So split zeros, when we have a leading zero and the rest, we say, okay, we call it with the rest, and then we increment. Again, this is our thing where we're accumulating state. So we start by counting 0 zeros. If we see a 0, we count one more 0 and proceed. Okay. If we get to, so if the byte string doesn't begin with a 0, this case will fail. And we start with rest, and we say, okay, number zeros, and it flips the arguments because I was lazy, but if we wanted to be a little bit clearer, we would return the rest and num leading zeros. It doesn't matter a whole lot. Okay. Okay. The number of bits in the rest is the bit size of rest. So I wrote this code a long time ago, and so I'm trying to remember. I'm reverse engineering how it works on the fly. Okay, that's right. So now what we're doing is that thing I mentioned where so the first thing was the step of handling the special case where we have a bunch of 0 bytes at the beginning of this string. Now we're doing this blue line step. That's what this line is the blue line step. Okay. Blue line step. Okay. This is saying we're considering the entire thing as one number, and it is, that's all this is doing, is decomposing that and saying we're considering all of this as one number. I think I could have said byte size of rest / byte. It doesn't matter. Anyway, zeros in base 58. So we're taking, so how do we encode leading zeros? Again, remember how I said that what base 58 does is it removes these problematic ambiguities like 0 and capital O. So I think capital O is allowed and 0 is not. And so when we want to represent the digit the digit 0 in base 58 is 1. Let me look it up. Let me see. It's not similar to Base64. It's the same. Okay. Right. So this is. Okay. This is from the original Bitcoin source code, which I believe was written by Satoshi. And so this is the entire set of digits. And there's 58 of them. So yeah, so lowercase l is gone. We have the digit 1, 2, 3, 4, 5, 6. I'm just looking for L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, A, B, C, D, E, F, G, H, I, J, K. No L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, and then the pluses and slashes. So again, here. Why base 58 instead of standard base 64 encoding? Don't want O, O, I, L. Ah, yeah, there's no I. There's no uppercase I. We don't have lowercase l that look the same in some fonts and could be used to create visually identical looking account numbers. A string with non-alphanumeric characters is not as easily accepted as an account number. Email usually won't line break if there's no punctuation to break at. Double-clicking selects the whole number as one word if it's all alphanumeric. Right, so that was the thing about double-clicking. Okay, right. Okay, yeah, so that's the alphabet. So 0, so the digit corresponding to 0. Again, 0 basically in our notation indicates an empty place. So 1, 0 means 1 times 10 plus 0 times 1. Right, so okay. We'll get into this. So our leading zeros, we say the character 1. So this is not the number 1, this is the character 1. This is a list comprehension. So this just means, so list seek, here, let me just show you. It just, that's all it is it just creates a sequence. So how this many leading zeros, we create that many 1 characters. So by convention, a bunch of digit or a bunch of character 1s, however many of those are on the beginning of the Base58 encoded string, the text, that's how many leading 0 bytes there are in the byte string. Okay. The rest in Base58 is the result of encoding. Right. Again, this is we're calling our, yeah, so we encode the rest using enc2, and then plus plus just means concatenate these 2 lists. Okay. So enc2. All right. So I think at this point, it's time for me to explain the quotient-remainder algorithm, because that's what this is. And I'm hoping that I explained it in that post. Otherwise, I'm going to have to pause the video and think about how to explain that. All right. All right, the quotient-remainder algorithm. So this is an algorithm for converting a pure integer. Like I said, in math, we think of an integer as not being necessarily having a concrete canonical representation in any base. That's a sort of a human thing. As far as math itself is concerned, all bases are equal. So let's write the number 1, 2, 3, 4 in base 10. So 1, 2, 3, 4. Okay, this is kind of confusing. So what I'm doing is converting base 10 to base 10. So 1,234 is 123 times 10 plus 4. So this is 1,234 divided by 10. So integer, this is integer division. So, and this is the remainder when dividing by 10. So 1,234 divided by 10, div just takes the integer part here, and remainder doesn't quite, remainder is the remainder when dividing by 10. Okay. Uh-oh. Okay. Okay, so 123 is 12 times 10 plus 3. So the quotient here is 12, the remainder is 3. So this is 12 is 123 divided by 10, and 3 is 123 modulo 10. 12 is 1 times 10 plus 2. This is 12 divided by 10 is 1. 12 modulo 10, or remainder, divided by 10 is 2. Okay, and then 1 is 0 times 0 plus 1. So 0 is our quotient, 1 is the remainder. So basically our sequence of remainders here picks off the digits in reverse order. So here we're doing the remainder dividing by 10, and the sequence of remainders tells us the base 10 digits in reverse order. So we get 4, 3, 2, 1. That's our sequence of remainders if we just repeatedly divide our number by 10. If we want our base 58 digits, we repeatedly take the remainder when dividing by 58. And that'll give us our base 58 digits. Okay. So base 1, that doesn't make any sense. And if think about why. That's what mathematicians say when we can't think of why. It's an exercise for you. So we have to handle 0 specially. Right, okay, because... Okay. So the digits of n in an arbitrary base and then our accumulator. The quotient is n divided by the base. The remainder is n remainder of the base. So this is 1, 2, 3, and this is 4. If n is 1, 2, 3, 4, and base is 10. Our new n is q, and our new digits is r prepended. Because remember, we get the digits in the reverse order, so each new digit we put at the beginning of the string, and the result will be the digits in the correct order. Okay. So our new digits, we take the digits we already have, and we put the new one at the beginning. I hope that's big enough. And then we call digits again with our new n, so n is bigger than 0. We're not negative numbers are annoying, and we don't have to worry about them right now. Digits with our new number, the base remains the same, and our new digits. Okay, and when we get a quotient of 0, that tells us we're done, and we don't have any more digits. Okay, that is why we have to do this stupid thing where we handle leading 0 bytes, because otherwise, if we took, let's say, if we didn't do special handling of the 0 bytes, what would happen is that, let's say we have this byte string, and so that's byte string X, and then byte string Y is the exact same byte string, but there's a leading 0 byte. If we didn't have the special way to handle the leading 0 byte, these two byte strings would encode down to the same Base58 representation. And then when we decoded it, there would be an ambiguity. We wouldn't know how many 0 bytes to add. And so it would be possible that you could encode something and then decode it. Your decode procedure would have to make a choice. It would probably just pick don't add any 0 bytes. And then when you encode and then decode back, you would lose information. You would actually get back a different result, and that's really, really bad news. We want our encoding to be perfect. Okay. So what am I looking at? Oh, we're here. Okay. So let's walk through the call chain for digits 1, 2, 3, 4, and 10. So this is notional code. So the first case is successful on digits 2. So digits 1, 2, 3, 4, and 10 when 1, 2, 3, 4 is bigger than 0 and 10 is bigger than 1. So we call digits 2 of 1, 2, 3, 4, and 10. So up here, that's this function. So n is 1, 2, 3, 4, and base is 10. Okay. 1, 2, 3, 4 is bigger than 0. That's true. And 10 is bigger than 1. That's true. Okay, so now we call digits 1, 2, 3, 4 on with 10 and the initial accumulator of the empty list. General case, so this matches the general case of digits 3. So digits 1, 2, 3, 4, 10 when 1, 2, 3, 4 is bigger than 0. Cool. This matches, so we go into this case. So our quotient is 123, which is 1, 2, 3, 4 divided by 10. Our remainder is 4, which is 1, 2, 3, 4 remainder 10. Our new n is 1, 2, 3, and our new digits is 4, which is the remainder prepended onto our accumulated state. Okay. So the next thing we do is we call digits with 1, 2, 3, 10, and 4. General case of, and this matches the general case of digits 3. Digits of 1, 2, 3, 10, and 4 when 1, 2, 3 is bigger than 0. Cool. Quotient is 12. Our remainder is 3. Our new n is 12. Our new digits are 3 and 4, which is r prepended to 4. Our digits are 12, and then we call digits again with 12, 10, and our accumulated state is 3 and 4. Okay, we call 12. Is 12 bigger than 0? Yes. Okay. So Q is 1, R is 2, our new N is 1, our new digits are 2, 3, and 4. Then we call digits again. It matches our general case. And we go through exactly the same procedure here. Q will be 0, which is 1 divided by 10. R will be 1. Our new N will be 0. Our new digits are 1, 2, 3, and 4, which is R prepended onto 2, 3, and 4. And this is digits. And then we call digits again with 0, 10, 1, 2, 3, and 4. And then this matches the terminal case, because remember, we're checking if, so up here in our digits algorithm, it's going to ask, is 0 bigger than 0? No. Okay, now go to the next one. Okay, now we have 0 base. And so if we pass this a negative number, the program would crash. And again, in Erlang, we want that because it's a highly concurrent system. And so if a single process crashes, it's not that big of a deal. And it's better if the process crashes than if it continues with state that it's not supposed to have. Very counterintuitive if you come from the world of single-threaded programming. But again, this concurrency ends up making your life a lot easier, because what you end up doing is sort of separating out. In a single-threaded program, you end up doing basically braiding. So you have to take things that really should be a lot of threads and end up intertwining them. And in Erlang, because you can have multiple threads, you just have multiple threads. But what you don't realize the degree to which you have to kind of like fold in all of the different things your program is doing into one thread and have them all kind of share attention in a single threaded program. And in Erlang, you can just have them be multiple threads and your life is a lot easier. So if you have thing A talking to thing B and thing B talking to thing A, in a single threaded language, you basically have to kind of like, intertwine the two things. And in Erlang, they're two different processes. And then that way, if something goes wrong in thing B, thing A can continue. So again, now we're going to convert 1, 2, 3, 4 into base 58. So 1, 2, 3, 4, and 58. So on digits 2, first case is successful, so we go into our digits 3. Okay, we match on our general case, 1, 2, 3, 4, and 58. So 1, 2, 3, 4, it turns out that that is 21 times 58 plus 16. So Q is 21, which is 1,234 divided by 58. And 16 is 1,234 remainder 58. That's what this means. So this div in rem, what that means is that it satisfies this identity. 1, 2, 3, 4 is 21 times 58 plus 16. So in this case, Q is 21, R is 16, our new N is 21. So right now, by the way, there's two steps to this process. There's first figuring out sort of what the digits should be like morally, and then there's actually taking those digits and writing them as characters. Much in the same way that with like Base64, the first problem we had was figuring out morally what these 6 bits corresponded to numbers wise. And then there was the second problem of converting them to characters. It's just that was such a fast step, you didn't even realize there were 2 steps there. So here, the problem of discovering what these colored numbers are is actually a little bit harder. And so that's why Base58 is so much more tricky. Okay. So our quotient is 21, our remainder is 16, our new n is going to be 21, and our new digits are 16. So digits of 21 and 58. So again, in Base58, again, there's actually an extra step now that I think about it. I didn't quite realize this. But here, in Base64, maybe this is why it's so much simpler, is we can go directly from the binary, the bytes, to just morally figuring out what these numbers are. Whereas in Base58, we have this additional step of figuring out what this big number is, and then decomposing that into 58 into digits between 0 and 57. So R here so this number will always be between 0 and 57. And if it was 58 or higher, we would simply increment this number. That's the way that this works. Okay. So now we're going to call digits on 21 with the base of 58 and 16, and 21 is less than or equal to 58, so we're just going to get, so Q is 0, so 21 is 0 times 58 plus 21. Q is going to be 0, R is going to be 21, and our new n is going to be 0, and the algorithm terminates. So generally, bigger bases, because with a larger base, each successive number, each digit contains more information. And we'll talk about how to measure information. The way we measure information actually is the number of bits. We'll get to that. But again, so with a bigger base, each digit contains more information. So a single base 58 digit, it can encode between 0 and 57. So it has more possible values it can encode than between 0 and 10. So it has actually a larger quantity of information, and so therefore it takes fewer steps to how do I say this? We need fewer if we have a bigger base, we need fewer digits, and if we have a smaller base, we need more digits. So miscellany, yeah. Notice, oh, hey, I wrote that. Notice that with the larger base, the algorithm terminates in fewer steps, requires fewer digits. This is why we use large bases like 64 and 58. Converting the digits, right, to the proper base 58 text representation is a matter of looking up 21 and 16 in a table, and then it turns out to be NH, and then we decode N, that's 21. If we decode H, it's 16. In the special case where the byte string contains no leading 0 bytes, and its byte length is a multiple of 3, then these are indeed two instances of the same base N algorithm. Right. Base 64 is considerably faster because 64 has a power of 2, and therefore the algorithm can be written using bit operations, so without integer division. The idea of base 58 is to be, right, base 64 that guards against manual entry errors. So it excludes characters with visual ambiguity, so O and 0, IL, yeah, you get the idea. Or, yeah, breaking long lines or double clicking, I forgot about that. Because base 58 is so computationally expensive, I'm glad I mentioned this in March, it's generally only used for byte strings that have a small fixed size and where manual entry is likely to be a concern. So for instance, eternity public keys are always 32 bytes long and are likely to be communicated over email or on paper, or, entered manually. Base 64 is used for byte strings with a large variable or unknown size. Right, for instance, eternity transactions can have arbitrary payloads and are in some sense ephemeral. So you're not going to write a transaction down on paper. Like, you send the transaction into the blockchain, it's there in the blockchain, and that's the end of the conversation. Like, it's only relevant until it's on the chain, and then a blockchain, by the way, is just a list of transactions. Person A sent person B X amount of money, and that's it. And then there's a way to authenticate that person A actually authorized the transaction, and that's the whole public-private key thing, which we'll get to at some point. So in practice, yeah, that I mentioned this. We'll add a 4-byte checksum to the end of byte strings before doing base N encoding to guard against manual entry or copy and paste errors. So yeah, this is exactly actually how your account public key gets encoded. We compute our check bytes by taking the double SHA-256 hash of the bytes. Why we do the hash twice, I don't know, but we do. We pick the first 4 bytes off of that, and then we base58 encode the public key concatenated with the check bytes, and then add the AK prefix, and that's it. Yeah, so base58 is a two-step conversion. We like to think of binary as a sequence of ones and zeros, i.e. bits. Right, and I was saying this at the beginning of the video. But strictly speaking, it's more correct to think of a binary as a sequence of bytes. A byte has a value between 0 and 255. And if you're an electrical engineer and that what I wrote is wrong, you're wrong because we're programming, we aren't doing electrical engineering. A byte has a value between 0 and 255, which conventionally we think of as 8 bits, but really the bytes are what is real and the bits are a chimp brain fantasy. So when we're converting a byte string to base58, really it's a two-step conversion. Right, we're taking a binary, which is our base 256 representation of the number, converting it to an integer, and then converting it to a string. Right. Right, so this is a 256, base 256. This is a pure integer, or what is morally an integer, and then the string is base 58. And so our encode step, we're going this way, and our decode step is this way. Now, of course, under the hood, everything is really binary, and I mean binary, bytes, not bits. But at the Erlang and TypeScript level of fakery, the correct, or at least simple way to think about base58 is as a two-step conversion. Byte string to integer to text. I provided examples in TypeScript and Erlang because those are the two languages we use most commonly in Eternity. Luckily, both have built-in big num arbitrary size integer arithmetic. If you're doing this in a language like C that doesn't have big num arithmetic, yeah, you're going to have to interleave in the big num logic yourself. You know, have fun with that. So let's look at the, the video is going to be 2 hours long, but let's look at the code and then we'll get out of here. All right. So encoding, so backing up, we grabbed our leading zeros, figured out how many there were, put a bunch of ones, digit ones, or, you know, character ones at the beginning of the string, and then the rest, we're going to do exactly what we just did. So encoding, we have our bytes as a big num, and we have our state, accumulated state. This Erlang notation means a list of integers between 0 and 57, and the base 58 is going to be a string. Okay. So let's look at the general case first. So our quotient, you know, I should have put bigger than 0. Oh well, because it doesn't matter. So encoding our big number with our accumulated state, we calculate Q and R, and then we call encode again with Q and R prepended onto the accumulator. With Q and R prepended onto the accumulator. Okay, now when we get to 0, so remember back here when we were calculating digits. So again, we're sort of interleaving in two steps. First thing we do is calculate the digits, like the moral digits here. So when we calculated morally that the digits of 1, 2, 3, 4 in base 58 were 21 and 16. And then the next step is just looking up 21 and 16 in a table. So this part calculates the moral digits. When we encounter a 0, that means we have no more digits to calculate. And so now it's a matter of, for every digit in the accumulator, we're going to look it up in the table. What this says is go along the list, lists map, go along the list, and for each item in the list, apply this function to it and compute a new list, which is that function applied individually to every item in the list. And int to char is just the table that you expect it to be. So that's it. Okay. Okay. Decoding. Okay. So how does decoding work? Well, we're just going to be doing the same process in reverse. And in reverse, what we're going to be doing is taking, first thing, we're going to take these characters and convert each of them to the integer that they morally represent. And then we're going to take that sequence of integers and just take each number, multiply it by 58, and keep multiplying the number by 58 and adding the new digit until we run out of digits. Okay. So decode base58 to decoded bytes. So when base58 is a string and decoded bytes is binary. So we're converting a string is text, to binary data. So decode a base58 encoded string into a byte string. So decode the string. The number of leading ones tells us the number, right, the number of leading 1 characters tells us the number of leading 0 bytes. So this works exactly the same way that the other one works. So the number of leading zeros and the rest as a string. The leading zeros are, this is the exact same thing, but it's it's a binary comprehension rather than a list comprehension. The rest of the numbers, right. Right, so this is saying, so here, what we've done is we have, let's say, a bunch of ones and then a bunch of stuff that isn't ones. These ones say how many leading 0 bytes there are. We count out how many of those are. This says construct the byte string of leading 0 bytes. Okay, the rest of this is a bunch of, the rest str here. This is a bunch of characters. This is saying convert all of those to the, convert each of those to the integer that each character morally represents. So look it up in char2int, and those are the rest of the numbers. The bytes are decode the rest of the numbers, and our accumulator is 0. That's interesting. 0. Ah, that's right. So the state we're building up, right. I was confused because we're returning a binary here, but we're passing in as our state an integer. That was what was confusing me. But again, we're computing, we have this sequence of moral digits. We're saying, okay, what moral integers does that correspond to? Is that right? Right, we're going to say, what moral integer does that correspond to? And then we're going to say, how do I represent that moral integer as a byte string? Right, so again, we're base58 to moral integers to base256. That's what we're doing. We're converting base58 to base256. Okay. So, yeah, split ones, it works exactly the same way the other thing does. So decode. All right, so decode as an argument, it takes our list of moral digits, picks off the first digit, and says, and our accumulated, this is our moral integer. So this is the 7216575 here. That's the accumulated state we're building up. And so we're going to take that state, and each time we encounter a new digit, so you imagine we're decoding 1, 2, 3, and 4. Let's say those are our moral digits, and we're at like 1 and 2. Okay, we're gonna take that. Multiplying by 58 is the equivalent of shifting over by one place, in the same way that in our decimal system, multiplying by a number by 10. So if I take 36 and multiply it by 10, I get 360. So I just take the number and shift it over by one place. That's what multiplying by 58 does, in the same way that if I take 36 in our base 10 representation and multiply it by 10, it just shifts it over by one place. And then adding in n, so that gives us our new moral integer that we're decoding. Then we're decoding the rest of it. So we're calling our function again with our new built-up state. When we finally run out of digits, we have our final state. Okay. Big num to binary big E. Okay, big endian. I'm not going to get into endianness. Final accumulated number. Okay, so this here, we're taking our sequence of digits and converting it to a moral integer. So our Base58 digits. Here, we're doing our quotient-remainder algorithm. So up here in our encode, we were doing our quotient-remainder algorithm and building up a list of numbers between 0 and 57. Right, that was our accumulated state. And then at the end of it, we converted that list to a bunch of characters so that we would have a string. Here, we're basically taking our moral integer, doing the exact same quotient remainder algorithm, but we're building up a binary string, so a byte array. And again, that's a native type in Erlang. So much like this, when we encounter a 0, we're done. For the same reason that when we were converting 1, 2, 3, 4 in base 10 to base 10, when we encountered a 0, that says, okay, we're done. So we're taking our integer. Let's look at the general case first. Our quotient is the result of dividing the integer by 256, which is 2 to the 8th. The remainder is the remainder of dividing by 256. Our new accumulator, we take the remainder, our new digit, prepend it onto the beginning, and then call again with q and our new accumulator. And at the end of it, because our accumulated state is just binary, which is the return type that we want, then yeah, so we're converting the big num, the moral integer, to binary. And then big E means that endian means the digit order. So do we have, so what's interesting, our number system is called, in English, it's called the Arabic number system, or the Hindu Arabic number system. So for instance, this number we read as 39, and we think of the 3 coming first and then the 9. What's interesting about Arabic is Arabic's actually a right-to-left language. So in English, conventionally, we write our characters going left to right. I don't know if that's correct on your perspective, but left to right. And so when we read a number, we think of the bigger places as coming first. But Arabic is a right-to-left language. And interestingly, when they write down a number, they use the same digit order that we do. And so when the Europeans, when we copied the Arabs' number system, which they copied from the Hindus, the Arabs used little endian. So we use big endian, so the bigger places come first. But with the Arabs, the little places come first because they read right to left. It's interesting. I think little endian is a little bit is better. Craig disagrees, but he's wrong. All right. Jesus Christ, the video is going to be like 3 hours long. No, it's going to be 2 hours. That's not too bad. But I think we got through everything. I think we understand Base58 versus Base64, why you would want to do this. Yeah. Oh, I didn't get to TypeScript. Do I want to do TypeScript? Okay, let's just glance at the TypeScript code. Just so that you can... Ooh. I apparently forgot to... Yeah, so that's a mistake. I need to go fix that. Because here I remember... Yeah, so you can't quite see, but what I did up here So with the link that worked, I linked the specific commit. And with the link that didn't work, I linked to the branch. So let me just paste. Let's see if that works. Yeah, here we go. How do I zoom out? There we go. So this is Base64 in TypeScript. Let's just very quickly look over this. GitHub is GitHub is like, you know, it was like the perfect website 10 years ago, and then for some reason, anytime Microsoft buys something, they just turn it into absolute garbage by just trying to add all these stupid features that nobody needs. GitHub was a finished project 10 years ago. Okay. Base64 utility functions in TypeScript. Okay, so we encode the bytes. So what did we do? Okay, right. So the way that I ended up writing this in Erlang or in TypeScript was I said, okay, slice 3K. How does this work? Right, so basically the tail can be 0, 1, or 2 bytes long. And so instead of sort of doing the branching, you know, so when we're encoding, let's go up here. So instead of doing this sort of branching inside the function, all in one function, here basically I'm saying, okay, pull apart a byte string that I know is a multiple of 3 in length, and we're going to treat that separately. So our general case, this is going to be one function, and then our special case, we're going to handle each of these separately, and then, you know, GitHub. Okay, we're going to handle each of these separately. Okay, so encode the head. Would you knock it off? Okay, so encode the head. Let's see. Assume the length of bytes is a multiple of 3. Right. So what this does is says, okay, we're in the general case here. So we're encoding a byte string into Base64 that we know is a multiple of 3 in length. And so what this is doing is saying take 3 bytes. Right. Take 3 bytes off the beginning of the string, encode 3 bytes. That's what encode 3 is. And then continue. Okay. So encode 3 bytes. So here we have to do this nonsense with bit shifting, but it's the same basic idea as in Erlang. With encoding the tail, depending on the tail length, it can be either 0, 1, or 2. If it's 0, we're done. If it's 1, I'm not going over the TypeScript in a lot of detail because I don't think it illustrates the logic very clearly, and so this is mostly for just people who need the TypeScript to sort of ascertain the general structure of the program. Okay, so again, we're encoding 1, so encoding a single byte, we pull off the byte from the byte string. Number. Okay, so the right, we have to take the number. What? Oh, that's right. Right, so yeah, so we're doing exactly the same thing as in Erlang, but we have to do all this nonsense with bit shifting and moduli and whatever. And then, yeah, then we're done. Okay, in code 2, it's the same thing. Pull off the first byte and the second byte. Do all this bit shifting stuff to get your. Let's actually look at encode. Where's encode 3? So in code 3, get the first 3 bytes, and let's see. Right. So N0, N1, N2, and N3. And we have to calculate these by doing all of this bit shift nonsense. But fundamentally, that's all that this is doing. And then saying convert each of them to a character, and then return the concatenation of them. And then encode tail just does a branching based on how long the tail is, and then sends it either to, says, okay, if there's no tail, we just return the empty string. If there's 1 byte, we run encode 1, which, yeah, just does. So again, it's going to be A, B, C, D, E, F, G, H, a bunch of zeros. Encode them 2 equal signs. Encode 2, it's the same thing as in Erlang. Take the first 2 bytes, encode them into 3 characters, and an equal sign, return that. Okay. Say decoding. Length of the string is guaranteed to be a multiple of 4. If the string is empty, return the empty array. What? Right, this branching contains... Right, okay, so the bottom branch, the else, is going to say, if we get a string that isn't a multiple of 4, then we're going to crash. Okay. But if we... How does this work? Okay, if 4 is less than the length... Okay, not the length is less than 4. So if the length is greater than 4, so if there are more than 4 characters here, okay, then what do we do? Okay, so it's a similar thing. Okay, so up here we did this slice 3k thing, where basically I said, okay, I want to handle my general case in a simple function, and then I'm going to have a bullshit function for my bullshit cases. Here, I'm doing the same thing. So, in general, what am I doing? So what are my cases? If the length is exactly 4, or if the string is empty, so maybe let's go up. If the string is empty, I'm just going to return, so if I'm asked to Base64 decode an empty string, that corresponds to an empty byte array. If it's 4, then I'm going to call decode tail. Fuck off, GitHub. And if it's bigger than 4, and the length is a multiple of 4, I'm going to do my splitting thing. Oh, that's right. Oh, no. I forgot about this. I love JavaScript so much. Okay. Integer byte arrays don't have a concat operation for some reason. So, split the head and the tail. So, again, we have that branching for if we have sort of a normal tail versus a tail with padding. So in Erlang, in our decode operation, we have sort of 3 or more bytes remaining. So in JavaScript, we're splitting that up into more than 3 or exactly 3 bytes remaining. We're handling those separately. Fuck off, GitHub. Jesus Christ. All right. I hate this language so much. Let's see. Arrays. Okay. Right. Okay, so we decode the head, decode the tail, and then concatenate the two and return the result as a byte array. Okay, that's right. Yeah, this is a thing in JavaScript. If you take the array 1, 2, and 3 and the array 4, 5, and 6 and you add them together, you get the string. It's so... Why is the world this way? Let's see, decode a string that is known to not have any padding. Right, I bet... Okay, I bet decode tail checks how many equal signs there are. Ah, they both call down to decode 3. That's what's going on. Okay. So this goes 4 characters at a time, right? Decodes those 4 characters into 3 bytes, updates that into an accumulator, returns the accumulator. Okay. Decode tail looks at the last 2 characters, sees how many equal signs are there, which is implicitly what we're doing over here. We're up here in our decode. We're taking the last 2 characters. How many equal signs are there? If there's 2, we do this. There's 1, we do this. Over here, I gotta be careful where I click on GitHub because pop-ups. Microsoft just never learned their lesson from Clippy, did they? Anyway, so we take the last 2 characters. Are they both equal signs? If so, we decode 1 byte. If there's only 1 equal signs, we decode 2 bytes. If there's 0 equal signs, we decode 3 bytes. Okay. Decode a 4-character long base64 string corresponding to 3 bytes. Right. All right, so this is pulling each of those characters out into their own characters, converting them into numbers, doing all that nonsense of converting these binary digits to, instead of 4 groups of 6, converting that to 3 groups of 8, and then returning that as a byte array. Decode a 4-character long base64 string. Right. It's the exact same thing. Taking the 3 characters, converting them to numbers, doing all the bit shift nonsense. Take 4 characters into 2 bytes, converting them into numbers. Right, and then converting that into a byte, and then returning the byte, and then, is that it? Yeah, these are... Okay, yep. All right, that's Base64. Thanks, GitHub. Base58. All right, encode, number of leading zeros, the rest. We get make our ones, we encode the rest, and we concatenate the 2, count the leading zeros. That's just that. This could probably be made into a while loop. Generate a bunch of 1s. Encode a uint8 array that has no leading zeros. Bytes to big int. Okay, so we take the bytes, convert them into a big int. I think actually this is clearer, and then we take the big num, the big int, and convert that back down to base58 and return the result. So this makes it clear that there's two steps, whereas in Erlang it kind of folded them in together, but whatever. So convert a byte string to a big num. So if you suffix a number with the lowercase n in JavaScript, it makes it this big int type. So the accumulated big int. And let's see. Yeah, this is exactly this. So bit shifting left by 8 is the equivalent of multiplying by 256. That's what we did over here. And encode. Is this encode? Oh, right. Erlang just does this for us. Right, okay. Up here, no, it was down here. Where were we multiplying? No, when we were multiplying by 58. Okay. Remember when I said that when we had the number like 58 and I multiply it by 10, it's the equivalent of place shifting it by 1. Multiplying by 256 is the equivalent of place shifting by 8 bits or 1 byte. Okay. Let's see, what does this do? Plus big int of this byte. Right, so it just takes the number for each new digit. So this is taking our bytes in base 256 and converting it to a big int, which is our moral integer. And all that's doing is each time it gets a new byte, shift over. Is it doing that in the right order? Yes. Yes, it is. Bit shift over to the left by 8. Add in the new byte. And then finally return the accumulator. Oh boy. Convert a big int to base58. Oh boy. Okay, this is the same thing. So as long as q is not 0, we keep going. Let this n q mod 58, q divide by 58. Okay, so instead of JavaScript, I don't think handles recursion very well, so instead we use loops. I find recursion to be a lot simpler. So let this base58 character, right, big int to character. Right, so it's the same thing as so this is our big num to base58. Right, that's this right here. We're saying, so this is the equivalent of, well, q is not equal to 0. Divide q by 58, that's this line. R is this n. Oh, this is doing the implicit conversion to a string, so this is doing 2 steps at once. So here, we're computing our digits morally. Yeah, you know what? That would be a little bit more efficient, because this has to do 2 passes through the list. And this is folding it in. Yeah, so this way is, I mean, there's no way it's faster because the JavaScript runtime is insane. But this is a slightly more efficient. So here, we're building up our list of, moral digits, base 58 digits that we talked about. And then once we've done that, we're going back and for each one, converting them to characters. It would actually be faster instead of having to do 2 passes through the list. Now, again, we're only using these for small arrays. hopefully. And so, you know, this algorithm isn't designed with efficiency in mind, so we're only handling small amounts of data, so this doesn't really matter. But instead of doing 2 passes through the list, it'd be better to just do, whenever we calculate the digit, at that point, also calculate calculate the ASCII character, the text character that corresponds to the moral digit. That way we only have to do 1 pass through the array. So that's what's going on here. And then, again, we're doing mutable state and then returning it, decoding. Okay, same basic idea. Take the number of leading ones. Yeah, pull off the leading ones, pull off the rest. Base58 dot. Oh, it's not a module, it's that dot okay. Pull off 0. Okay, make our zeros, decode the rest. Our pre-result. Right, and then we convert it to a uint8 array. Okay. Count the number of leading 1 characters in a uint8 array. Okay, that works the way you expect. Generate a bunch of zeros for however many, yeah, whatever. Decode the rest. Okay, right. Convert base58 to big int to base256. Yeah, base58 to big int works. It's the quotient-remainder algorithm. So we take our base58 for character. Right. Multiply by 58, so that's shifting over 1 digit. Add in character to big int. All right, you're probably going to have to watch this video multiple times. Yeah, big int to base256. Yeah, so it's taking our, so this is taking our sequence of character digits. Again, we're only doing 1 pass through the list. Convert the character to whatever integer that character represents. Add it to the big int and return the big int. Big int to base256. Taking our big int and then doing our quotient-remainder algorithm to convert it to digits between 0. Yeah, so for instance, array reverse. Yeah, boy. Because push in JavaScript, that's right. Push adds to, so in Erlang, when we add an element to the list, we prepend it, and in JavaScript, it adds it to the end. That's just, and then so we build the list in the opposite order. Okay. Array reverse, so take the number, take the remainder divided by 256, update the quotient, push the new remainder onto our list of digits, reverse it, and return it. All right, and these are our translation tables, which work exactly the way you expect. Decode, okay. Jesus Christ, okay. 2.5 hour video. And then I get to edit all of this. That's going to be great. That's going to take the rest of my day. All right, bye.